From a Black Hills dark site in western South Dakota, good evening. I'm Richard Walker. On the Sky Tour tonight, the North American Nebula, NGC 7000, a large emission nebula stretching 90 light years north to south. Though discovered in 1786, it was only recently, in 2020, that its distance from planet Earth became known. Then, in the constellation Cassiopeia, NGC 281, the Pacman Nebula, a unique emission nebula due to its collection of high-mass stars, the type that are responsible for much of the energy pumped into our galaxy. It provides astronomers a unique opportunity, as these types of stars are typically obscured by gas and dust. Plus, the Gamma Cygni Nebula Complex. Deep within the Orion arm of our galaxy is a rich nebulous region surrounding Gamma Cygni, the supergiant star at the center of the Northern Cross. At 12 times the mass of our Sun and about 150 times its radius, its massive size has doomed it to explode into a Type II supernova. All that and more on Dakota Starry Nights from this amazing dark site. Strap yourselves in. So let's begin with taking a look at some of the components that make up an astrophotography platform. We still got a little bit of time left before it gets dark, so this will be a good opportunity to show you some of the basics at the observatory. Now, there are many configurations that you can pursue, and this time frame we have here is way too short to cover all of them. So we're basically going to cover a short focal length setup. One of the reasons is it's the easiest to master, and I highly suggest that if you're going to start out imaging, you start out with a short focal length. If you recall from episode 1, the differences between a short focal length telescope and a long focal length telescope is that the longer focal length telescopes have more power, a narrow field of view, and therefore are more difficult to learn how to master. And they also require longer exposures in order to get enough data to where you could start stacking the images. But we'll cover that in another episode. So, you might be thinking that the most important part of any astrophotography platform is the telescope. Well, actually, it's not. Although it's important. But the most important part is the mount. Without a good mount that's going to allow you to track across the sky accurately to where you're not getting elongated stars and problems with tracking, You need a good mount, and it's preferred when you're starting out to put the money into a good mount. That's where you want the money to go. Later on, you can always upgrade to a better telescope, an ED or a triplet or what have you. So you want to have a mount that's going to be able to grow with you. What's great about this mount, it does equatorial as well as alt-az, which you saw in episode 1. I had it set up with 2 telescopes, but now I have it in an equatorial mode. And the reason is for tracking, you need to be equatorial so you don't get field rotation from your stars. You really can't image in alt-az. You can't get the long exposures that you need for narrowband imaging or even broadband if you're working with a very faint target. Okay, so that was a short focal length platform, and what we have here is a long focal length platform, as it's pretty obvious. This telescope native focal length is 1122 millimeters in focal length. A short focal length platform and a long focal length platform are basically the same except for the optics, obviously. With this platform, it's a little more demanding, as I had stated earlier, because you're more on top of whatever target you're imaging. So any deviation in the tracking in the mount is going to cause elongated stars. There's essentially 3 ways to guide. Some astrocams have a guide chip inside the camera, and that eliminates having an extra camera exterior of the setup, which is kind of nice because what happens is you're looking through the same light path that the telescope is imaging at, and that's great. Another way to accomplish that is through off-axis guiding. You essentially take a little sliver of the light that's coming through the telescope and use that to make the computations and deviations in the tracking. Send that information to the guiding program in your laptop, which then sends the correction to the mount. And that's how that works. And the third way that is the easiest to get your head around is to have a telescope mounted on top of the imaging scope in a secure fashion to where there's no flexure or jiggle or anything like that, and then put a guide cam in here and essentially run the information through the same loop that you would if you were doing off-axis guiding. So to sum that up, what you need is a guide scope, a guide cam, an imaging cam, an imaging scope, and 2 software programs. One that will do the data acquisition, which is going to be from your imaging cam, and the other to do the computations from the data coming off the guide cam, and then sending those corrections to the mount so that your mount stays precisely on the target so that you can come up with a high quality image. Okay, I've got a couple of cameras here. One is a film camera from back in the day, and for you folks out there that don't know what these are, they required for you to load them with film. Everything was manual here. This is a Canon TL-QL, which was state-of-the-art back in 1970. Now, doing astrophotography with film is really difficult because you only really get one exposure and you don't have the ability to stack the images as we do today, or to be able to put them into a computer and manipulate the histogram and the different parameters that can bring out the fainter nebulosity. And now here is what replaced it. This is a DSLR, whereas this was an SLR, single lens reflex, digital single lens reflex. Now, if you have a DSLR and you're considering astrophotography, before you invest into one of these astrocams, I highly suggest that you start out with your DSLR and get a feel for what it's like to do imaging. These work really well if you're at a dark site and you're imaging galaxies, star clusters, and planets. They're good for that. And so you can really get your feet wet without having to invest into these other cameras. Now, the way these work is that you would remove your lens and you get what they call a T adapter. And this has the same threads that goes into your camera, locks in, and then you get this nose, which is a 2-inch nose, meaning it's for a 2-inch focuser. All of these cameras have a T-thread interface. That's pretty much the standard. And so you would take this 2-inch nose and screw it into this T adapter, and now you can load this into your telescope. You'd put that in there like that, and voila. And now you can shoot astrophotography with your DSLR to get a start. The main difference between a DSLR and an Astrocam is that a DSLR is uncooled, and having it cooled is advantageous because as you do a long exposure of 5 minutes or so, you start to build up heat, generates dark current, and all of that affects the image. By having a thermoelectrically cooled camera, you could reduce that noise and calibrate your images for high quality astrophotography. But I have shot images with this DSLR on a cool October evenings and gotten some pretty good results at a dark site. Now check out this Andromeda Galaxy that was shot with this camera. The exposures were like 2.5 minutes, and I shot probably maybe 40 minutes worth of images and then stacked them, and those are the results. So these do work well on cool nights. In the hot summer days, they don't work so great, but in the cool fall and in the winter, you can get some good results using a DSLR. Here we have two cameras with the same sensor. These are CMOS cams, and these are made by Zwo. They're a pretty popular camera company. The difference here, besides the size, is that this one is thermoelectrically cooled. That's what this fan back here is for. And this one is not. Should you get a cooled camera versus an uncooled camera? If you intend to doing astrophotography, then yes, you should get a thermoelectrically cooled camera. However, if you're going just to do planetary imaging or solar system objects and you intend to use this as a guide cam, then no, you do not need to have it thermoelectrically cooled. Finally, one of the more important questions you might need to ask yourself is, should you go with a color cam or should you go with a monochrome camera? The answer to that question is, it all depends on where you intend to image. If you have access to dark skies, then you can get some really fantastic results with one of these thermoelectrically cooled color cam cameras. But if you're like most of us and you live where there's a moderate to severe light pollution, you're going to be better served with a monochrome camera. And the reason is, with a monochrome camera, you could use narrow band filters. They only allow a specific type of light to come into the sensor, and they cut out all the light pollution, or the vast majority of it. So that will allow you to image inside the city. Now here's an image of the Horsehead Nebula that I took inside the city. So narrowband imaging really allows you to image from your backyard or your front yard or your garage and get some really fantastic results. Now there is an alternative to a monochrome camera if you're using a DSLR, or better yet, an astronomy camera that's thermoelectrically cooled. And that is, there's a new type of filter produced by OPT, a triad filter, and Optolong also makes a similar filter called the L Extreme. Now these filters use a narrowband filtration that is optimized for color cameras. And if you're using a DSLR, you can get somewhat respectable results from either one of these filters. However, it is recommended that you try this during the cooler times of the year, in the fall or the winter, where your DSLR is going to be operating under cold ambient temperatures, thereby reducing the thermal noise that will most certainly occur if you try using these narrowband filters during the summer months. Because of the narrow bandwidth that these filters have, it takes for longer exposures, and the longer exposures generate heat. Well, all right. When we return, we'll head on up to the Gamma Cygni Nebula Complex and IC 1318, the Butterfly Nebula. See y'all after sundown. God, I love this place. Woo! Okay folks, this wasn't on the menu for tonight, but I decided first thing before I even went to any nebulous targets was to go to Jupiter. Jupiter and Saturn are up right now, and believe it or not, right now there is a transit on Jupiter. And below the transit, where you see the shadow, the giant red spot, and then over to the side is Ganymede. It's like a trifecta of incredible planetary observation. It's amazing. I've seen Io transits and Europa transit. This one is following right along the equatorial belt, and right on the edge there below it is the giant red spot. Pretty amazing. I'm going to try to image it, guys, but I don't know if it's going to really come through. I could see one of the moons and I could see Jupiter in the lens here, but planetary, you really need to do like video on planetary. Let's see. I think it's just too bright. I'm gonna try for video. Maybe a guy can get lucky with that and stack it. I don't know. This is really amazing. See, now this is through the 102 millimeter f11 refractor. And it is just crazy beautiful. No halos, no glow. And it's not a triplet. This is a doublet with an ED lens element in it, but because of the longer focal length, like I had said earlier, it really cleans up any chromatic aberration. Okay, that's it for that. I don't know, guys, if we got it, but there it is anyway. Oh man, it's just gorgeous. Jesus. Wow. It's about 1/3 of the way across the planet right now. I get lucky with this. The last time I was at another dark site last year with this refractor and bino views and caught the Europa transit. And Io was just right at the edge of the Jupiter here. Both of them actually, Ganymede and Io both, a perfectly round super jet black dot, you know. Wow. Cool. All right. All right, man. Geez, man. Right there. It's worth the whole night. You know what I'm saying? I mean, that's the cool thing about, you know, astronomy. You get a moment like that and you pull in something like that and it's worth everything. I mean, how many people get to see stuff like that? It's just amazing. Pretty cool. Well, I'm going to move on now, show you what's up there in the constellation Cygnus, the Swan. Cool. Boy, it got a little chilly there. I had to put on this coat. I mean, man, I don't know. We're out here in the wilds of South Dakota and the temperature could just drop on you all of a sudden. All right, well, that Jupiter transit was just awesome. So let's go to Cygnus, IC 1318. I know I have an IC catalog here, 1318. And the Butterfly Nebula. Enter. Cygnus is pretty high. Geez, it's almost right there at zenith. Yeah, she's straight up, real high. I hope it doesn't hit that leg. Yeah, okay. Yeah, look at that. I mean, that's almost zenith. All right, let's see what we got. Get the chair. I don't think I'll need this. I don't even think I'll need that. Probably just this one. I'll get the hand controller. Let's see what we got. Oh yeah, sweet. Wow. Oh wow, this is really beautiful. Oh geez. You know, this is the first time I've seen it with the shorter focal length. I've seen it with the Dob, which is a longer focal length, but this is great. This gives you like the whole butterfly. You could really, well, not the whole, but the body, the main body, and the two wings, and Cedar right in the middle. Awesome. Check it out. All right, here we have the central part of IC 1318, the Butterfly Nebula and Gamma Cygni in night vision. Okay, so here we have a 14-image mosaic with Gamma Cygni, commonly known as Sadar, located left of IC 1318, the Butterfly Nebula. Now, this is a beautiful and extensive diffuse emission nebula surrounding Sadar. Sadar is not part of this nebula. It is actually a foreground star located halfway between us and IC 1318. Now, Sadar marks the center of the Northern Cross in the constellation Cygnus, and it's classified as a supergiant. Now, we're looking deep into the Orion arm of our galaxy in this image, and the nebula is more than 3,000 light years from us. Now, compared to our Sun, seen here during the 2017 total eclipse, Sadar is an enormous star with 12 times its mass and about 150 times the Sun's radius. And it's emitting over 33,000 times as much energy. Back to the mosaic capture, because of its relatively high density, it is believed Gamma Cygni has only recently attained supergiant status, reflecting an ongoing inflation of its atmosphere, having left the main sequence of stars. Now, the fate of Sadar, in theory, is sealed because of its mass. Typically, supergiant stars of this size evolve into a Type II supernova after developing an ion core by fusion of heavier and heavier elements and resulting core collapse. Now, other notable deep sky objects in this region of the sky is NGC 6888, the Crescent Nebula. Now, this project required 18.5 hours of narrowband hydrogen alpha data due to the extensive size of the capture. So if you're considering astrophotography, but are concerned about the complexities of narrowband color integration, it's rather easy to start out with just a HA filter and shoot monochromatic images. And hey, you know, if it was good enough for guys like Enzel Adams, then it's good enough, right? Okay, well, that's really, really cool. I really enjoyed that. Definitely amazing. I mean, it's right up at zenith, so you can really see it clear. And yeah, I'll tell you, wow, this is a great night. I mean, between that transit just a little while ago and now, this beautiful view. Well, okay, let's move on to the Pacman Nebula. Let's see, NGC 281, I believe. There we go. There we are. Okay, for this one I'm going to need my stool. I like this little puppy because it's adjustable. Okay, let's see. Yep, there it is. Pacman Nebula. Okay, here we are at the northwest corner of the constellation Cassiopeia, the Queen. And NGC 281, an emission nebula affectionately known as the Pacman Nebula, so named due to its resemblance of a popular video arcade game of the 1980s. If you're familiar with the game, you can make out the resemblance in this night vision view. Now, what makes NGC 281 unique are its high-mass stars. These types of stars are important because they are responsible for much of the energy pumped into our galaxy over its lifetime. You know, unfortunately, these stars are poorly understood because they are often found relatively far away and can be obscured by gas and dust. The stars within NGC 281 are the exception to the rule, though. Now, here's a narrowband image I captured of NGC 281 with a total integration of 7 hours and 30 minutes of data. Now, located about 9,200 light years from Earth and almost 1,000 light years above the plane of the galaxy, NGC 281 gives astronomers a nearly unfettered view of the star formation within it. In the center of the Pacman is a star cluster designated IC 1590. Now, IC 1590 is a collection of hot, young, blue supergiant stars. And despite the wild conspiracy theories on social media, are in no way a reference to some X-rated movie. Now, astronomers have used the Hubble Space Telescope to study this open cluster within the Pacman, pictured here in this NASA European Space Agency Hubble image. This image only shows the central part of the nebula where the brightest stars at the core of the cluster are found, with part of the Pacman's hungry mouth visible as the dark region below. Now, there are multiple generations of stars located within the Pacman. The present idea is that something externally triggered this baby boom of stars. But Pacman isn't gobbling up these stars. Instead, the nebula's gas and dust are being used as raw ingredients to make new stars. However, the stars in IC 1590 are still plotting their escape from the Pacman Nebula, as open clusters are only loosely bound together, and the grouping will eventually disperse within a few 10 of millions of years. All right, well, let's move back to Cygnus and the North American Nebula, and again, we're going to be like right up at zenith. Geez, it's straight up. It's beautiful. The swan, that's the tail, and then it's running down that way, and then the wings are going out like that. And right on. Stars, telescopes, and coyotes. Oh, God. Oh, boy. I tell you, I love it out here. I love it. I'll tell you what. So, like I was saying, I got the Milky Way running down that way, and Cygnus with the wings like that, and then Vega is right over here, and the Ring Nebula is right there between Cygnus and Vega is the ring. So, yeah, Jupiter, Saturn, Aquila, Altair, everybody's here. All right. And there's Ursa Major, the Big Dipper, commonly known as the Big Dipper. And of course, Polaris right there. Love it. Okay, well, let's go to the North America Nebula, NGC 7000. It awaits, it awaits. All right. Boy, those coyotes were cool. I love them, I tell you. I don't know, for some reason, they always remind me of a Walt Disney movie or something. I don't know why. Okay, let's see. View object, all right. Here we go. She's going to be straight up. I mean, look at that. It's, woof. This would be a good time to image it. Yeah, let's see. Okay, right there is denim. So, yeah, it's going to be, yeah, right there. So that would be about right. Yep, that's it. Well, okay, let's check out the North American Nebula. Oh man, that's it. Perfect. Check it out. Wow. Okay, the North American Nebula, NGC 7000. Now, it's famous for its shape, which bears a striking resemblance to the North America continent. NGC 7000 is a large emission nebula located in the vicinity of Denham, the brightest star in the constellation Cygnus. Now this guy is huge, stretching an incredible 90 light years north to south, and was discovered by William Herschel in October 1786. Now here it is in narrowband. Now this took 14.5 hours of data and an STF 8300 monocam. And that scope, by the way, was a 92 SS-TNB triplet that was designed by Thomas Back, who is no longer with us. A fantastic scope. But anyway, it would take more than 100 years after its discovery for it to get its name, when the pioneering work of a German astrophotographer, Max Wolf, who in 1890 noticed this nebula's characteristic shape on a long exposure photographic plate and dubbed it North American Nebula, as pictured here in this European Space Agency Hubble image. It took even longer, though, 234 years to be precise, before the distance would be known, when in 2020 it was measured at 2,590 light years away. Now in this section, called the Cygnus Wall of NGC 7000, is where the highest concentration of star formation is occurring, and the easiest feature to spot with a telescope. Now here it is in night vision. It spans about 20 light years and appears in the part of the nebula that resembles Mexico and Central America. The identity of the star that iodized the nebulous hydrogen, causing it to glow, was long uncertain and suspected by some to be Denham, as the North American Nebula lies only 3 degrees east of the bright star. However, it is the hot, massive 6-magnitude binary star HD 1995-79 that is responsible for setting the nebula aglow. This star is also known as Nero's Diamond. Now, NGC 7000 typically cannot be seen without binoculars or a telescope because it has a low surface brightness. With binoculars or a small telescope, it appears as a fuzzy patch of light. Now, the best way to observe it is with some kind of filtrations, such as a UHC or contrast boost filter or an O3 filter, or better yet, with night vision as seen here, and a hydrogen alpha narrowband filter. Well, that's going to do it for this evening. I sure had a lot of fun here. I hope you did too. If you like what you saw, consider becoming a member. Until next time, clear skies. Thanks for tuning in to Dakota Starry Nights, and please, y'all stay safe.